All right, and so for part A of the problem, we derived an equation to describe the difference between Cp and Cv. And here it's in terms of temperature, dp dt, constant V, and also dV dt at constant P, right? And so we went through all this work to get an equation like this, but it still looks kind of weird. We still have partial derivatives in here, right? So why is this useful? The nice thing about this analysis that we did here is, if you could look on the page, at no point did we make any sort of assumptions, right? We didn't assume ideal gas. We didn't assume van der Waals gas. We didn't assume something was incompressible, right? And so this relationship we derived here, Cp minus Cv, this is true for any sort of fluid or any sort of chemical that we're dealing with, right? And so if we want to get precise information about a specific system, what one would need to do is actually go out and plug in. That you would plug in equations of state into these partial derivatives. And that's how you would actually get an equation that described your specific system, right? And so for the rest of problem 5, that's exactly what we're going to do, okay? So if we take a look at part B for problem 5, it asks us to show that for Cp minus Cv, it wants us to show that this difference is equal to R for an ideal gas, right? And so this is an assumption that we made before. But now, with this sort of general equation, which applies to everything, we want to show specifically the result for an ideal gas. Okay? All right. So from the ideal gas law, we know P is equal to RT over V. So if we took the partial derivative of P with respect to T, constant V, it would just be R over V. And similarly, if we rewrote the equation so that it was explicit in V, and then took the partial derivative of it, constant P, we would get that dV dt at constant P is equal to R over P. All right, and so if we go back to our Cp minus Cv equation, what we have is T times dP dt, so R over V. Okay, and then that is multiplied by dV dt, which is equal to R over P. Okay? All right, now the nice thing here, if we take a look at this first term, or if we take a look at T and multiply by R over P, so let me rewrite this so it's a little bit more clear. So we have R over V here, and then we could regroup the equation so that we have an RT over P here. From the ideal gas law, we know that if we switch these two things, we know that V is just equal to RT over P. So what we have now is R times V over V. Those cancel, and we're left with R. Okay? And so that's why, if we assume we have an ideal gas, then the difference between Cp and Cv would just be the gas constant. Same as what we assumed before. Okay. All right, so that's, a proof of why the difference between the heat capacity, the constant pressure, and the constant volume heat capacities for an ideal gas is just equal to a gas constant. All right, so that's how we could apply that Cp minus Cv equation for an ideal gas, but we could also apply it for liquids as well. Okay? All right, and so in part C of this problem, it wants us to derive an expression for Cp minus Cv in terms of these named derivatives. This isobaric expansivity, this isothermal compressibility, and also pressure, volume, and temperature. Okay. All right, so alpha V is equal to this. and kappa T is equal to this. Okay? Alright, and so these are the definitions of alpha and kappa. Right, so this one has a dv dt constant p in there. This one has a dv dp at constant t. But if we take a look at our equation here, we do have a dv dt there, right? So that we can immediately tell that's going to be related to our alpha v. But here we have a dp dt at constant v, right? So that's not directly in terms of the any of alpha or kappa. But what we could do in order to rewrite our equation in terms of alpha and kappa is we could once again go back to the triple product rule, but we could apply it in a backwards way, right? And so what I mean by that is if we take dp dt constant v, we could expand it out using that triple product rule. Okay, right? Because v goes into the numerator of all the partial derivatives, and then we cycle through with p and t. All right? And so the nice thing about doing it this way is now we could rewrite dp dt in terms of this partial derivative, which is related to alpha v, and this partial derivative, which is related to kappa t. Okay? In fact, if I write that out here, well, actually, I'll save it for the next step. All right, and so if we take a look at Cp minus Cv, what we have is temperature. And then we could, for the dp dt term, we could plug in this. And then multiply it by another dv dt constant p that was already in the equation. Okay? All right. And if we combine everything, it's a negative squared divided by, let me move this down a bit so I have more room. Okay? All right, and so we have our equation like this. In fact, I'm going to move the negative sign in here so it becomes even more obvious. And so what we have here, we have negative 1 over dv dp at constant t. So if we take a look at here, that's the same thing as saying that we have 1 over molar volume kappa t. Okay? And this dv dt squared that we have, that's the same thing as saying alpha squared molar volume squared. That comes from just rearranging this equation. So if we plug in alpha and kappa, what we get is temperature alpha v squared over kappa t molar volume squared. These cancel. And for Cp minus Cv, we get that in terms of the compressibility and the expansivity, our equation simplifies down to this. Okay? Alright, and so, that was a little bit of work. And so why is this useful? Well, now that we have the CP minus CV equation into this, as I mentioned before, alpha can be measured through experiment, and kappa can also be measured. Right, and so if we just knew the values of alpha and kappa, then we could actually try to quantify what the difference between CP and CV are. And that's what part D of the problem asks us to do. Okay? So it asks us, to evaluate how good is the assumption that CP is equal to CV for a solid. Right? And so it asks us to do this for aluminum, where the values of alpha and kappa T are known, and also that molar volume as well. Okay? Oh. Should be molar volume in this final result. I knew I was missing something. Okay? Alright, so for part D, what we want to do is actually just plug in some values. So alpha V is equal to 2.3 e to the negative 5 inverse Kelvin. Kappa T is equal to 0.014 gigapascals. And then molar volume, which is equal to 1 over rho, is equal to 1 over 2.7 centimeter cubed per gram. Okay? Alright, so we have all these values. So what we want to do now is just plug them in. Okay? Alright, and let's assume, we're dealing with 300 Kelvin. Temperature at 300 Kelvin. Okay? Alright, so for CP minus CV, we have T, which is 300 Kelvin. We have our molar volume, which I'll do some unit conversion. To make this a little bit easier. 1,000 gram per kilogram. And then we have our alpha squared. Okay, and then we want to divide that by kappa, 0.014 gigapascals. So that's e to the 9th pascals, which we know a pascal is a joule per meter cubed. Okay? Alright. And so, when we write out this equation, we get that CP minus CV ends up being 4.2 joules per kilogram Kelvin. Okay? So that's the value for CP minus CV. But is it big or is it small? Well, to get an idea for how big or small it is, we could actually just take a look at the constant pressure heat capacity value for aluminum at 300 degrees Kelvin, or 300 Kelvin. And when we do that, we see that CP is 902 kilogram Kelvin. So that's much larger than the 4.2 we got from CP minus CV. And so, for that reason, that's why when dealing with aluminum or a lot of different solids, people feel okay and feel justified with just assuming that CP is equal to CV.